Again, welcome to Biostatistics 1. Today's our main objective is to start with the inferential statistics. So this is our first topic in inferential statistics. Our main objective, again, is to understand the concept of inferential statistics. Also, what is a sampling behavior of a mean, what is a sampling behavior of a count, and also a proportion. Now, the concept of inferential statistics is trying to use the sample to make a decision on a population. As we all know, it's very difficult when we're going to do a research or a studies and get a data from a population. One reason is that population is very large. It takes time to get a whole data from a population, and also it will take some money, or in this case, a funds involved. So because of that, anytime we are doing research, we always trying to take a sample from a population. So an example, we have 1 million male between the age of 20 to 30 in New York City. And we want to study, let's say, the weight or obese about them. Well, we don't want to take the whole 1 million population. We may take a sample of 10, 1,500 in a month from the 1 million. Now, when we are taking a sample, so we have to make sure that the data is well represented, which means we want to avoid or remove any bias in the data set. So here we have a diagram showing there's a sample and a population. So we can see that the population is a very large. So the first step in inferential statistics, we want to do some studies, maybe test some hypotheses. And the first thing we need to do is to collect a sample from the population. So we can see the sample is very small. Then we study the sample. We can test the statistics of the sample. Then the decision we get on the sample, or the result we get in the sample, we are going to apply it to the population. So the characteristics of a population is called a parameter. So the parameter here again means the characteristics of a population, such as the mean of a population, the standard deviation of a population, etc. And also statistics here means the characteristics of a sample. So example, and the mean of a sample, and the mean of a sample, or the standard deviation of a sample data is called statistics. So here we say we are very curious about parameters in the population, and we always calculate the statistics in the sample. So now what's the difference between the parameters and statistics? We know parameters comes from a population. So do we calculate it? Of course, no. So the parameters are not calculated, and they are constant because we have a population. Population is 1, so the mean, standard deviation, proportion always is constant. Now with the sample, which is the statistics, characteristics of a sample, we always do the calculation. And also the values or the statistics of a sample are not constant. I may take a sample of 10 people from a population of 100, and I may find the mean weight or age of the sample. Now I can take a second sample from the same population, and I'll find the mean weight or the age again. Now these two samples, average, age, and weight may be different. They are not going to be the same. So here we say that the statistics are not constant. So here we have the mean, standard deviation, proportion. So here we say, how precise does a given sample mean reflect underlying population mean? Now, in order for us to answer this question, we must establish the sample distribution of X bar. Now, the sample distribution of X bar is the hypothetical distribution of means from all possible samples of size n taken from the same population. So the concept here is that, for example, I have 10 items, a population, 10, and I'm going to take a 2 sample of 5, which means I'm going to use all the population. Now, if I find the average of the population, the sample, the 2 sample, and I find the average of the 2 samples, the answer will be the same as the average or the mean of the population. So again, I have 10 items for the population. I took 2 samples, 5 and 5. I find the mean of each sample. So I have 2 mean of 2 samples. Then I find the average of those 2 means. The answer should be the same as the population mean. And that is the concept of sample distribution of X bar. Now we have a simulation here. For example, we have a population, the size is 10,000 with a log normal distribution, which is a positive skew. The mean is 173, the standard deviation is 30. Now we take a repeated simple random samples, each of n equal to 10, which is the sample size is 10, from the population of 10,000. We calculate the X bar in each sample. Then we plot the X bar, which will be in the next slide. So what we're trying to say is that I have 10,000, the population is 10,000. And if I take the sample of 10, it means I have to take 1,000 samples. Now, if I take 1,000 samples and I find the mean of each sample, our distribution will be a normal distribution of the sample means. And this is the concept of what we call the central limit theorem. Even the population distribution is not normal, but since we take the mean of each sample and we use all the population, here we have a population of 10,000, we take 10, and we can take 100, 10 times or 20, 100 times, etc. The goal is that we are going to use the whole population in our sample. This time we are taking sample without replacement. So if the size is 10,000 and I'm taking a sample, let's say the sample size is 1,000, then the possible samples I can have is 10,000. Or I'm taking a sample of 10 and I have 10,000, that means I can take up to 1,000 samples. Now the sample values, if I plot them, the distribution again will be normal. So that's what we have here. We have our population distribution, which is almost normal, but again, there's no symmetrical here. There's no symmetry. But if I take the sample from the population and I use all the population, take a sample without replacement, and I find the mean of each sample, the distribution will be normal distribution. And it will be symmetrical. And also if I find the mean of all the sample mean, the result will be the same as the population mean. So we can see here we have it on the center. So that's the finding here. We say the distribution B is normal. When we say distribution B, we mean this section is normal. Even if population distribution, which is distribution A, is not normal. And that's what we call the central limit theorem. Second, also, both distributions are centered on the mean. There's no any bias here. So again, when we find the mean of all the sample mean, it will be the same as the population mean. Then also the standard deviation of the distribution B will be much lesser than the standard deviation of distribution A. This is what we call the square root law. And we can even see from the graph, we can see that the distribution B is shrinking very small, while distribution A is wide. So this means the standard deviation of the population distribution A is larger than the standard deviation of distribution B. And actually we have a term for it. This will be the standard deviation of the sample, which is called the standard error. and it's equal to the population standard deviation divided by square root of the sample size. So as the sample size increases, again, our standard deviation for the sample will be lesser, smaller. So those are the three findings we have from the sample distribution of mean. Distribution B, again, is normal, even though distribution A is not. This is central limit theorem. Both distributions are centered on the mean, which means, again, there's no bias, and also it means the sample mean of all the samples is equal to the population mean. So that's again the result from the simulation experiment. As we said earlier, the finding one is central limit theorem. The reason why, as we said, the distribution will be normal for B, the sampling distribution of the mean will be normal. And also the mean of the population is same as the sample distribution. So here we said that central limit theorem says that the sample distribution of S bar tends towards the normality, even when the population distribution is not normal. Then the second, we said there's no any bias, which means the expected value, which is the mean of the sample, is the same as the population mean. And the second, we say the square root law, which says that the standard error or the sample standard deviation is equal to the population standard deviation divided by square root of the sample size. So that's what we term again, the standard deviation of the mean. It's also called, we have a special name, which again we said is also called SE, which is the standard error. And as again, the standard error is equal to the population standard deviation divided by square root of, again, the sample size. So we have an example here. In this example, it's a data set on adult intelligence score. Based on the values we have, the data, we find out the standard deviation is 15. Now, if we take only one sample, we can see that the standard deviation of the population is the same as the standard deviation of the sample, because we are using all the population. So if we are taking only one sample, it means it will be the whole population. The sample size only one. Now, as the sample size increases, we can see that the standard deviation will, again, of the standard deviation of the sample will decrease. So here, for example, we have from 1, now we have 4. The sample size is 4. So it will be 15 divided by square root of 4, and that will give us 7.5. Next, we increase it to 16, which means it will decrease more. So we have 15 divided by square root of 16, and that gives us 3.75. And what we're trying to say is that as the sample size increases, again, the standard error or the standard deviation of the sample will again decrease. So putting all together, we said we have our X bar, our sample mean. Our sample mean always will be a normal distribution, and the sample mean is the same as the population mean, but the standard deviation is standard error, which means, again, standard error is the standard deviation for the sample. So here we say the sample distribution of X bar is normal with the mean of mu, population mean. And the standard deviation will be standard error, which is the standard deviation of the sample, which is the population divided by square root of n. So as n gets larger, the standard deviation of the sample gets smaller. So this first again makes inference about mu possible. So let's look for example here. Here, let's say we have let X represent adult intelligence score. with a normal distribution, and the mean is 100, and the standard deviation is 15. Now we take a sample size of 10. So when I take a sample size of 10, the mean will remain the same, but this time our sample standard deviation will be 15 divided by square root of 10, the sample size. So here we can see that based on the size here, we have a normal distribution. The mean is constant. But we can see that again, the standard deviation of the sample is 4.7. This will take us to 68% of sample mean will be in the range mu plus or minus standard error. And here we have the rule for 68%, 95%, 99.7%. And we talk about this rule, I think, in chapter 5, unit 5 lecture. So 68% is always one standard deviation. So the mean plus or minus. Now 95% will be the mu plus or minus 2 standard error. Then 99.7 will be the mu plus or minus 3 standard error. That's the range of the data. Now we can see from figure 2 that the population distribution, the standard deviation is very wide, very 15, very large. So, but we can see that distribution of the sample mean is a normal distribution, but we can see that the standard deviation is very small, so it's shrinking. So that will lead us to a law of large numbers. We said that as a sample gets larger and larger, the sample mean tend to be closer and closer to the population mean. And this is the tendency known as law of large numbers. We see an example here. Let's say we have a sample size as our x-axis. We have the mean of the first n observation as y-axis. We can see that when the sample size is only 1, we can see the fluctuation. It doesn't, again, the center vertical horizontal line here is the mean, population mean. So when the sample size is very small, we can see that the sample mean is different, it's fluctuating. But as the sample size increases, somewhere around 1,000, we can see that it's getting close to the population mean. When we reach 10,000, again, 10,000 is the population size. When the sample size reach population size, they need to be exactly, and the mean of the sample will be the same as the population also mean. So sample behavior of a count and proportion, we can recall from unit 6 that binomial random variable represent random numbers of success x in n independent, and also is binomial. So the output or the outcome always is success or failure, true or false, yes or no. So we know in binomial random variable represent a random number of success in n independent, success or failure tries. Now the probability of success for each try is called a P, and then the failure will be Q, which will be 1 minus P. So in binomial notation, the random variable x is in binomial form with NP. N is the number of try and P is the success. Now the sample distribution of x of 10 and 0.2, again, 0.2 is the probability of success, 10 is the number of tries, is shown on the next slide with a mean of 2. How do we get the mean 2? Because we know in binomial distribution, the mean is equal to NP, the number of tries times the probability of success. So N is again 10, P is 0.2. So 10 times 0.2 will give me 2. Now, if I want to find the standard deviation in a binomial distribution, it will be N times P times Q. So it will be 10 times 0.2. Q, since P is 0.2, Q will be 0.8, 1 minus 0.2. Then the answer we get, we square root it. So we can see the sample distribution of count and proportion illustration here. So we have the number of success and also the proportion. And also we have the each probabilities. Now, there's one thing we can do. Sometimes we may have a question whereby we have a binomial and we want to do normal approximation to binomial. This is only possible depending on the sample. So as the sample size gets larger, the binomial distribution will take on a normal properties. And normally they give us a condition here that if the number of try n times probability of success times probability of failure, if the value is greater than or equal to 5, then we do our normal approximation, which means the binomial will take on normal properties or normal distribution properties. So we always have to do our test first. NPQ greater than or equal to 5, then we have a normal approximation, which means our binomial will take a normal distribution form. But if NPQ is less than 5, then it will remain binomial distribution. It can't take a normal properties. So this example given to us, we have x equal to, again, this is binomial lowercase b. And in binomial, we have our NP, which is n is the number of tries, 10. P is the probability of success, 0.2. So NPQ will give me 10 times 0.2 times 1 minus 0.2. The answer is 1.6. So since it's less than 5, we cannot apply a normal approximation. It will remain binomial. Now in the second option, we can see that the sample size increased from 10 to 100. So 100 times 0.2 times 0.8 gives us 16. And since 16 is greater than 5, we can say that we can apply the normal approximations, which means the probability distribution will take on normal form or normal properties. So here it depends on the sample size. We can see it's 10 year, but it's 100-year increase. So these are the formulas for normal approximation for binomial count. We know from our unit 6 that in binomial distribution, the mean is NP, which is N is the number of tries, P is probability of success. And the standard deviation is a square root of NPQ. N is again number of tries, P is the probability of success, Q is the probability of failure, which is always 1 minus P. Now, this is for binomial. Now, when it takes on the normal approximation, then we have normal distribution, NP, then the standard deviation. We know in normal distribution, two most important parameters we need is the mean and also the standard deviation. When we have the mean and the standard deviation, we can do our testing, for example, finding the z-score, then finding the p-value using the standard normal table. So we also have the normal approximation for binomial proportion. Again, the previous one is binomial mean, binomial count. And then we have the binomial proportion. So in binomial proportion, we did this previously in the unit 6 again. If it's proportion, the mean is always the same as P, the probability of success. And the standard deviation will be P times Q over N, square root. So when we take it to again, normal approximation, then we get normal distribution. The mean is P. The standard deviation is square root of PQ divided by N. So let's see an example here, a normal approximation to the binomial example. Here we can see that we have some count from 8 to 32, and it's actually a normal distribution. And we have some probability values from 0.00 to 0.12. Now we say suppose the prevalence of a risk factor in a population is p equal to 0.2. We should take a simple random sample of n equal to 100 from this population. The variable number of cases in the sample will follow a binomial distribution with n equal to 20 and p equal to 0.2. N equal to, they give n is again the number of tries. So if I'm finding the mean, it will be, again, we saw the n is 100, the p is 0.2. So that will give us the 20. Now, if I'm looking for the standard deviation to be square root NPQ, from the question, again, they gave us the mean to be, it should be somewhere here. The mean is 100. Oh, okay. No, sorry. We have the, the mean to be 20 because we have the n to be 100, p is 0.2. So to find the mean is 0.2 times 100, which gives us 20. And that's what we have, 100 times 0.2, 20. The standard deviation will be square root of NPQ. So n again is 100. If p is 0.2, then q is 0.8. So we have 0.8. The answer is 4. So this will take a normal distribution of the mean 20 and the standard deviation 4. We can do the same to our proportion. We have the data already. We know p. So if we know p, and we can know q, and we know n is 100, p is 0.2, so q is 0.8. With proportion, mu is the same as p, so the mu will be 0.2. With the standard deviation to be square root of pq over n. Since p is 0.2, q will be 0.8 divided by 100, and that gives us 0.04. So our proportion, we get normal distribution with the mean of 0.2 and the standard deviation of 0.04. So this is another example we have here. There's a statement of a problem. Our problem is, suppose we see a sample with 30 cases. What is the probability of seeing at least 30 cases under circumstance? Example, probability of our random variable s is greater than or equal to 30. Because we say at least, so it will be 30 or more. Assuming we have a normal distribution with the mean of 20 and also the standard deviation of 4. So this takes us to chapter 7 when we're doing the normal distribution for probability. So here we know that they have given us the mean and they also give us the standard deviation. And our random variable is 30. So this means I can find my z. So my z will be my random variable 30 minus my mean over standard deviation, which give me 2.5. Then I will go to the standard normal table to go and find the p for 2.5. Now when I get the answer, because we are looking for greater than or greater or equal to 30, we go to the, we shade to the right side. So it's shaded to the right side. So the answer we get is from the left to the value. So which means whatever answer we get, we subtract from 1, and that will give us our solution. So that's why the probability is very small, 0.0062. Again, the z of 2.5, we go to the table, it will give us some value. Then the value we subtract it from 1, we get 0.0062. So here we say our normal approximation suggests that only 0.0062 of sample will see at least this many cases. And that will be the conclusion for this section. Again, the last example we did, this is exactly the same as our lecture number 7, which was just the previous lecture. This is lecture number 8, unit 8. So we know that in the normal distribution, the two most important parameters is the mean and the standard deviation. Then any if I find the probability of any random variable number, in this case is 30, then I'll find a z. So the z will give me 30 minus the mean, which is 20 divided by the standard deviation. Z-score formula always is x minus mu over standard deviation. Now, when I get 2.5, we go to the standard normal table. Go to the left side, look for 2.5. At the top should be 0.00 because it's only 2.50. The answer you get, since it's greater than or equal to 30, we subtract the answer from 1 because always the table will give us a value from the left to the actual value. And I'm looking for greater than 30, so it will be the right side. So I'll subtract the answer I get from left to the value 30 from 1 to get the rest, because we know total probability value again is 1. So again, thank you for your time, and we're going to, next lectures, we are going to cover the hypothesis testing using the z-score as our test statistic. Thank you. Wish everybody the best.